Okay, hi everyone. Welcome to the Simons Institute. I'm Shafi and I'm the director at Simons here. And there's a thing you always hear, and that is that we are dedicated to research in theoretical computer science, especially collaborative research. And you're part of this, I think, amazing effort. And really our primary use of the Simons Institute and their programs to explore the algorithmic thinking in science and engineering, and I guess to study the laws of computation itself. So I'd like to welcome you to today's workshop, the graph limits, non-parametric models and estimation. And I think this is the first workshop on the graph program, right? We had a boot camp, and this is the first workshop out of 3. And it's organized in collaboration with Randomness in the Netherlands. And I'd like to really thank the organizers for their help and work, actually not help, they do everything. The organizers of this program in putting together a great program, and these are Suvik Dara, Christian Borg, Sophia Olid, and Marco der Hofstad. For my own purposes, who's who? You are. Okay.
I'm sure nice to meet you.
Very good. And Christian, I know, but he's not here. Okay, so I'd like to cover just a few logistics topics for this coming week, and then I'll pass the baton to Suvik. So food is given before the first talk and during the breaks. You're not supposed to bring food or drinks besides water into the lecture hall. And in order to show you what food means is this, I was not supposed to bring this. I was not supposed to bring it, now you know. And I will never do it again. What?
That's a good example.
Isn't it? It's sort of kind of a contradictory manner, but you will remember this introduction. And for lunch, you're on your own, but there are a lot of great places around here. One of my favorite is Rice and Bones. There's also in the law school, which is to this direction, and the business school in the other direction. And again, we ask you to leave food out of the auditorium. There are lockers. I don't know if you've seen them on the side of the building. For those who don't have offices on the first floor, if you'd like to leave valuables there. Our videographer who's sitting over there is Omid, and Omid Farr, and he will help speakers during the talk. If there's any problem, just kind of signal him, although the truth is he's always sort of on watch of what's happening. And our staff person is Elizabeth Ewan over there. Elizabeth was in charge of this workshop and all the logistics. And I guess in terms of this is hybrid, this workshop, all of our workshops have been hybrid recently. So I guess people in the audience just raised their hands, and the people online, somebody has supposed to monitor their Q&A. So I'm going to hand over things to Suvik, you, now that I know, and welcome everyone. And I hope you have a great workshop and fruitful research. Also clap for the organizers. Let's clap again.
Right. Welcome. Let me start by saying thanks to you for participating in this workshop. So this is the first workshop in graph limits. So over the past years, as you know, the limits of large graphs has become important across diverse disciplines and in science and technology, and graph limits is like the core concept that has been used to advance questions in statistical physics, statistics, probability in different fields, right? So we are lucky that in this workshop, we have speakers who have developed these fields, and we'll be listening to them and learning about modern challenges in the field. So the workshop will have approximately 3 to 4 different themes. The first theme is graph limits and its applications to combinatorics, and then applications to stochastic processes and applications to statistics. And there are new emerging topics in the disciplines such as graph on games, graph neural networks, and we'll be hearing about those topics. So we believe this workshop will be the ground for interdisciplinary collaboration in graph limits, and will take the field forward. So Remco, Christian, we have been trying to get together a meeting like this on graph limits for a long time now, since 2019, but the previous workshop at Urandom had to be canceled, unfortunately, due to COVID-19, but we are really glad that we could come together at the Simons Institute and this workshop could be organized jointly with Urandom. Okay, so let me say that in my experience in the Simons Institute, the talks are super interactive. So if you have questions in between, please feel free to participate and ask the speaker. The talks are approximately 40 plus epsilon minutes, where epsilon is between 0 to 5. So the speaker can, at around 40 minutes, the session chair will tell the speakers that, okay, you have 5 minutes left. The speaker can then wrap up and take questions, and we can use that to also transition between talks. Okay. So do you want to say anything else, Christian, Remco? No?
Sophia is part of the organizing.
Yes, Sophia is part of the organizing team here. Okay.
Sophia got COVID and they're sort of still very tired from it. Sort of she recovered at the same speed as Shafi, so she is not coming. She was here, actually wanted to stay, including the workshop.
Okay. Then let's start with our first speaker today, Péter Csikvári from Eötvös Loránd Institute and Péter Institute, and we'll be learning about random cluster models on regular graphs.
Thank you very much. Thank you for the invitation. It's a great pleasure to be here. This is a joint work with Ferenc Bencs and Márton Borbényi. Ferenc Bencs is my former PhD student, now postdoc at Amsterdam, and Márton Borbényi is my current PhD student. This talk is in the realm of statistical physics, so it's an application of graph limit theory to statistical physics. Okay. So what is the partition function of the random cluster model? So every statistical physical model has a partition function. Here, if we have a graph G, then we do the following thing. We take all subsets of the S set, and a weight of a subset is Q to the number of connected components of this subset, including the isolated vertices. So if there are isolated vertices, this is a connected component itself. And W to the number of S set. If you met random cluster model as a percolation model, then W is P over 1 minus P in that model. Okay, so why is it important, this whole model? And there are many different answers. And one answer for me as a combinatorist, but I will show that for a statistical physicist, it is also very important, that it is actually just a reparametrization of the so-called Tat polynomial. So Tat polynomial is a bivariate polynomial where we have an x minus 1 times the number of connected components of this set A minus the connected components of the original graph times y minus 1 to the number of connected components plus A minus the number of vertices. The way I can remember these quantities is the following. Suppose that the graph G is connected. The first one is 0 when A is connected, so it contains a spanning tree. The second one, this is 0 if A is a forest, so it is contained in a spanning tree. So these are sort of competing with each other, these two powers. Okay, and as you can see, you can easily convince yourself that this is really just a reparametrization. So if you know the number of connected components and the number of edges in each A, then you of course know this polynomial. So there is a parallel story in combinatorics and in random cluster model. In combinatorics, it counts a lot of things. So at 1, the Tat polynomial computes the spanning trees, here spanning forest, connected subgraphs. This is simply to the number of edges, but it counts some strange things also. So TG20 is the number of acyclic orientations. So we orient the edges and we see whether there is a directed cycle, and if there is no, that it's good, it's an acyclic orientation. And TG02 counts the number of strongly connected orientations. And also a specialization of the Tat polynomial, the chromatic polynomial, the flow polynomial. So it really counts a lot of combinatorial objects that are of interest. In statistical physics, the parallel story that actually this generalizes a lot of models. So most probably you have heard about Ising model, but which is the case Q equal to 2. But if Q is any positive integer, then this is the so-called Potts model, and the general Q, W, and Q is bigger than 0, and W is bigger than -1. This is the random cluster model. Okay, so there are two parallel stories, and I think this makes this whole concept really important. Actually, Grothendieck also arrived to this concept in algebraic geometry. Is there any question? And feel free to interrupt me whenever you want. Okay, so what's the problem I would like to study today? So we consider the following problem. Let GM be an essentially large graph sequence. So it means that this means that if you say count the number of triangles, then it's negligible to the number of vertices, also the number of 4 cycles, the number of 5 cycles, and so on and so on. So this is the essentially large graph sequence. And now let GN be a sequence of essentially large graph sequence, and I would like to compute this limit. One application of it is the following. So if you take a random deregular graph sequence, then it is an essentially large graph sequence. So it's true that for every fixed k, if you consider the number of cycles of length k, then it's negligible to the number of vertices. Actually, it converts to the Poisson distribution for each k. So it's very strongly essentially large graph. Of course, if you just don't like this essentially, then think of a large graph sequence. So the length of the shortest cycle tends to infinity.
If your graphs are random, you need to zero in probability almost surely what you need.
So it will be converged almost surely. So it converges very strongly. Okay. Okay, so what do we know about this problem? So Dembo and Montanari solved this problem for Ising model. And actually, they solved a much more general problem. They don't insist on having regular graphs, but they consider this essentially a large graph condition. They call it locally tree-like because if there are no short cycles, then the graph is locally tree-like. And then Dembo, Montanari, and San solved this problem for the Potts model. So when Q is a positive integer, except when W belongs to an interval W, W1, where there was some problem. Yeah, so there is an interval where you have to, it's harder to understand the Gibbs measures. So Dembo, Montanari, Sly, and San then solve the problem when D is even and Q is a positive integer. So the missing case here is only when D is odd, say 3, and W belongs to this exceptional interval where it is a bit harder. And then Helmut, Jensen, and Perkins solved this problem when Q is very large, And also they needed some explosion property about the graph sequence. There is a case which is also very important when we count graph colorings. This is a bit tricky in the sense that here this is a W is -1, so it's negative. So they solved it. And very recently with Ferenc bench, we solved it for the Tat polynomial when x is at least 1 and y is between 0 and 1. So it actually, as a special case, it solves the number of spanning for S and acyclic orientation. So some problems where it is not very trivial. Okay. So this is our main result. So we solve this problem when Q is at least 2 and W is non-negative. And the claim is the following. So the limit exists. So this is one part actually. And then we can compute the limit explicitly. This is ln PDQV, which can be computed as follows. Take this rather well ugly trigonometric polynomial. It's not that ugly actually. So take this trigonometric polynomial and compute it on the -pi interval, and that will be pi dqv, and then plugging back, and that will be the limit. Okay. Well, this trigonometric polynomial is a bit funny because it's a linear trigonometric polynomial raised to the d's power. So the d only appears here in the exponents. So this is the claim. Is there any question about it? So we can compute very efficiently this limit. Okay. So there is a phase transition. If you fix Q, it turns out that if W is smaller than some critical value, this critical value here, then this limit is actually quite simple to compute. This is Q times 1 plus W over Q to the d half. When the W is bigger than WC, then we get a strictly bigger quantity. So this picture somehow summarizes what we know about this problem currently for non-negative xy. So this is x and this is y, and Q is x minus 1 times y minus 1. So it's a hyperbola here. So Q equal to 2 is here. And so this talk is about this region. This region is our previous result with Ferenc bench. And we also know this region as a byproduct. We get it for free because of the other two results. Okay, so we see what is missing. Yes?
So when you have the phase transition calculated?
Yes, so here it is first order, except at this point on Q equal 2, where it is second order. For the easy model, it's known that it is a second order. Everywhere else, it's a first order. That's what every other hyperbola.
And these formulas that you show, are they linked to duality?
No. So I will speak about the proof, and from now on the talk will be a bit more technical. I know that it is a bit more technical. Actually, the first part will be quite easy to follow, this approximation of the partition function. So the idea is that first we try to come up with something which approximates ZGQW in a broad sense. So you will see this approximation is not really a very good approximation. It's just good for tree-like, locally tree-like, so essentially large graph sequences. And the second part somehow that we try to understand this approximation. The first part will be, I think, easy to follow. The second part will be a bit more technical. Don't worry if you lose something. Okay. So let me speak about this approximation part. So I will try to approximate it with a spin model. So what is a spin model? So in a spin model, we have a symmetric matrix N. It encapsulates what's going on the edges, and we have vertex weights. So when this is an R by R matrix, what we do is the following: we write all different vectors on the vertices. We evaluate at an edge what we get if we plug in, say, color 2 and color 3 here. Then we have an N2, 3 here. We also get a mu2 at this vertex and then mu3 at this vertex. Okay, so this is a spin model. Generally, it's much easier to handle spin models because they are sort of local. You can see at every vertex what it contributes to the whole graph. Okay. Unlike with connected components, if you have connected components, you don't really know at the vertex whether how it contributes. Okay, so when we have a post model, this corresponds to the matrix when you have 1 plus W in the diagonal and 1 the off diagonal, and we have 1 everywhere. And it turns out that this spin model has the same partition function as the random cluster model for this positive integer Q. Okay. So let's try to approximate this whole thing. And for a moment, let's assume that Q is a positive integer. This will give a motivation. So as I said, the post model has this matrix. And let's try to approximate with this very simple looking one where we have write 1 plus W over Q everywhere. So the sum of all entries is the same here and here. But of course, when we compute the partition function, this one, then each edge will contribute a 1 plus W over Q. So this is 1 plus W over Q to the number of edges. And we can write the colors in Q to the number of vertices way. So this is completely trivial to compute. So I will call it the rank 1 approximation. And this makes sense even if Q is not an integer. We can evaluate it when Q is positive. Okay, so the first very easy lemma is that if Q is bigger than 1, then this is actually a lower bound. And if Q is between 0 and 1, this is an upper bound. And the proof is really one line. That if you have a subset of edges A, then the number of connected components is at least the number of vertices minus the number of edges. So you plug in this lower bound if Q is at least 1, and you get exactly this quantity by binomial identity. So in some sense, it says that it is a natural approximation, although it's not good always. Okay, so how to make a better approximation? And of course, the previous one was the rank 1 approximation. We have the rank 1 matrix. Now let's try with the rank 2 matrix. Let's try the following thing. We keep the first row and first column, and then instead of this, we take this average, W over Q minus 1, 1 plus W over Q minus 1 everywhere. So again, the sum is the same in this matrix as the sum of the entries here. Okay, only we change this little bit. And then we can compute this as follows. Well, if we look at which vertices has color 1, then it will be some S. Then those edges will give inside the 1 plus W to the number of edges inside this set S. Then the rest will contribute this one. So the number of edges in G minus S 1 plus W over Q minus 1, and we can choose the rest of the coloring in Q minus 1 to the number of vertices minus S. So this is the same. Okay. And again, the good news that it makes sense if Q is bigger than 1. So we can forget this motivation with positive integer Q. This makes sense for every Q bigger than 1 and Q bigger than 0. Okay. And So of course, this is again a spin model. We have 1 plus W for color 1. We have a 1 plus W over Q minus 1 for the rest. We just call it the rest. And this rest has a weight Q minus 1. So the vertex weight is suddenly hit Q minus 1. And then we can write this way. So this again, the same format. Okay, so what do we know about this one? First of all, I need a lemma for the original partition function. So it says that for the original partition function, we have the very same identity as before, only without the one approximation. Now, this is true for the following reason. This is true for positive integer Q. Just think about it as a matrix where again the color 1 has, on S we have color 1, on the rest we have the other colors, Q minus 1 colors, and we have the same W. So this is true for positive integer Q, but on both sides we see polynomial, so this must be true everywhere. Okay. So if for integer Q, it is easy to see. For other Q, this follows from having polynomials. And then we can use the previous lemma to prove that if Q is at least 2, then we have this rank 2 approximation is a lower bound, and between 1 and 2 it's an upper bound. So that's why we have result about Q at least 2, because we need this lower bound thing. Okay, now the main result in this section that actually not only we have a lower bound, but we also have an upper bound, which is the following. So fix some G, count the number of cycles at most G, that be L, and then an upper bound is Q to the N over G plus L times this rank 2 approximation. Okay, so why is it enough for us? Because if we take the logarithm and divide it by the number of vertices, then this will be 1 over G times logarithm Q plus L over N times logarithm. Now 1 over G tends to 0 if G tends to infinity, and this L over N also tends to 0. So this is enough for us. So it's not a very good approximation, but it is quite enough for our purposes. Okay, so this way we see that if this limit exists for this rank 2 approximation, then the original limit also exists. Question? Okay, so let me sketch the proof, because actually the surprising thing that the proof is very short, only 2 slides, 3 slides with this picture. So let's understand this picture. So we see a subset of the edges, so the bold edges, and then we see various connected components, on 3 vertices, a connected component on 4 vertices, on 1 vertices, and a connected component on 2 vertices. And I will call a connected component large if it contains a cycle. Now, this is clearly large, but this is also large because the connected component actually contains this triangle. So it's large even though the set here does not contain a cycle, but the induced connected component does contain a cycle. So this is a large one, and these are small. Okay, so large if it contains a cycle, small if it's not. So I will call the set of large connected components LA, the set of small connected components SA. And finally, I need the concept of compatible vertex set R. This is just the union of some small components. It might be empty. So here, a small component is this one, or this together is a small vertex set, or the empty set. Okay, so these are the compatible ones. So let's try to gather some easy observation. The number of connected components is just the sum of the large connected components plus the small connected components. So the large connected, I claim that the number is at most N over G plus the number of short cycles, because a large connected component either does not contain a short cycle, but it contains a cycle, so it has size at least G, or it contains a small cycle, and the number of small cycles is this LGG. Okay, so the number of large connected components is can be bounded easily. Now, we need also this binomial identity. It is really just Q to the number of small connected components is the sum of Q minus 1 to the, well, the number of some small connected components, but the union of some small connected components was a compatible set. So this is just a binomial identity. It's nothing else. And then we can do the following. First, we bound these large connected components using here n over G plus L. This LGG is the same as this L. Then we get this one. Then we write this binomial identity here. And now what happens if I change the sum? So here I have a connected, here I have a compatible set. It contains some small connected component, and the complement is some large. On the large, we don't know anything. It can contain cycles or not, so I don't care about those part. So if I sum up for the complement, then I just get everything, 1 plus W to the number of edges, because I don't know anything about the complement. On the other hand, on the R, this compatible set, I know that we should see a forest. We should see a forest because it does not contain cycles. So the A itself does not contain a cycle. So when we sum up for R, we see a number of connected components of some subset D, which is a forest with some sum. Okay, so we arrive to this bound, and now the inner sum is quite easy to bound. So if we have a forest on a set, then we know exactly what's the number of connected components. This is just the number of vertex set minus the number of edges, because it's a forest. Okay, so here the number of connected components, I should write that on vertex R is R minus D. Okay, and then if I forget that this is a forest, I can get a binomial identity, and I get this one. So if I go back, now I managed to give an upper bound for this part, and then we had this contribution from the complement of R where we don't know anything, and we have this contribution here, which is just the one approximation, and this together is the two approximation. This is really the two approximation, and we are done. So maybe it was a bit fast. It's not the best way to present it on slides, but as you can see, this is very short, 2 slides and a picture. And here I didn't use regularity, so it might be useful for instance, Erdős-Tényi graphs, G and C over N. So that might be a useful stuff. Yes?
So I mean, even Erdős-Tényi graphs could be approximately regular, right? But here you don't use any regularity.
No, I don't use any regularity.
So could your mechanism be pushed to, for example, if you assume the degree distribution converges?
If it is essentially large first, then yes. Yes.
So heuristically, this must be somehow related to that your rank 2 approximation is exact on trees.
Yes.
Explain that a little. So why is the rank 2 approximation exact on trees? I mean, this gives a proof, but I want to understand it more heuristically.
Well, for trees, yeah, I'm not sure that I can give a good heuristic why it is immediately clear for trees. Unfortunately, I don't know a good heuristic. Practically, the big idea is really this decomposition to large sets and small sets and small connected components, and then the small connected components really behave like trees, and then is there any question about it? Actually, for trees, what you really get is that so for locally tree-like thing, this is okay. For trees, actually, already the rank one approximation is precise because it's a regular matrix. This 1 plus W and 1. Yeah, so already the rank one would have been enough for trees. Okay.
When the rank 1 and the rank 2 win.
Yes, this is the phase transition. This is what I showed. That
The phase transition is exactly where they start.
so I had this WC, and below this is the rank one actually. This is just the rank one, because if you raise to the number of vertices, this is q to the number of vertices, this is the number of edges. So yes, that's exactly the phase transition I mentioned. Yes, very good question. Okay. Okay, now I will analyze this two-spin model, because we have now a very specific two-spin model, 1 plus W, 1 plus W over Q minus 1, 1, 1, and weights 1, Q minus 1. Now, actually, the only thing we use about it, that this is a ferromagnetic two-spin model, so the determinant of this 2 by 2 matrix is positive. That's the only thing we use about it. But here I use regularity. Probably regularity is not really important, but for us it will be quite convenient. Okay. So we have this very specific two-spin model, this rank 2 approximation, and we want to prove that for essential algebraic sequence of irregular graphs, this limit exists. Now the fun fact that this is actually done. So we could have finished our paper on page 10, I believe. So the point is that this was done by Dembo and well, okay, this is a bit tricky to explain the story. So practically, it follows from the work of Dembo and Montanari, but explicitly it appears in a paper of Science Sun, because they work with easing model, but Science Sun shows that on regular graphs, every two-spin ferromagnetic two-spin model is equivalent with the easing model. Okay, so we could have finished it. These are the papers of this group. These are really fantastic papers. So we learned a lot from them. We also learned what kind of thing didn't work for them. So we try to avoid those things. So they always try to understand the Gibbs measures on this graph models, and there is a limitation, or at this point it seems that there is a limitation of this approach. So we directly try to attack the partition function and avoid Gibbs measures. Okay, so this is the result of Science Sun, which is actually just using the paper of Dembo and Montanari, that if we have a positive definite matrix N, so N is positive definite matrix, mu has positive entries, then there exists a PD and mu such that this limit holds. And then, of course, this is true for random irregular graphs. So this is for every essentially algebraic sequence. Now, I will show a stronger statement in a minute, and I will explain how to prove it. So this is the result. And actually, two things are true. If you know what is a Benjamin-Ishram convergence, then you can forget the locally tree-like condition. It's more general to have a Benjamin-Ishram convergence graph sequence. So then it's also true for Binomial convergent sequence of deregular graphs. We have a limit. Of course, to compute the exact limit is a bit tricky, unfortunately. The other thing.
But isn't it the same? Having a Benjamin from limit that is the regular graph and basically having for sure.
But
No, because it doesn't, I mean, for example,
for large
ZD half has a lot of cycles and it has a Benjamin trend.
yeah, so for a grid is a Benjamin
It's not a regular tree. Okay, I see.
yeah. So here we are at short cycles. That's very much
Short cycles.
Yeah. Yeah. The other thing, which might be a bit surprising, that we computed this PDN mu for the infinite deregular tree, so the locally tree-like graph. Now this is a lower bound for all deregular graph G. So we always get this as a lower bound, and it turns out that if the graph G contains a large number of short cycles, so at least epsilon times the number of vertices cycles of length G, then we get an exponential improvement on the partition function. So what we get is really a lower bound actually.
So among the PD is that rank 2 or rank 1 approximation?
Here, this is a general 2x2 matrix. So N is a 2x2 positive definite matrix, and our rank 2 approximation was a special case of it.
But it's off the tree.
Yes, yes, exactly. That's important that we can do it for. Yeah, so this is a lower bound, and it contains a lot of short cycles. Suddenly we have an exponential improvement.
Is it also the case here that you can loosen the regularity?
So in case if you lose the regularity condition, then you can't write here a PDN mu, but instead you have to write something which is called a beta approximation, and with this beta approximation it's true.
Does the limit also exist?
That's a good question. That we don't know. Yeah, it should be true, but I didn't prove it. So okay, so how to analyze this thing? And this is a bit technical, but actually not terrible technical. So again, we start to introduce a new function, and I call it the subgraph counting polynomial. So here I sum up for all subset of the edges, and for a subset I compute what's the degrees at particular vertices, and then I introduce this new variables x0, x1, xd, and then I plug in this product of x, the degree at the corresponding vertex. So let's consider a special case. Let's say the complete graph on 5 vertices. It's 4 regular, so we have variable x1, x2, x3, x4. In the empty subgraph, every degree is 0, so this will contribute x0 to the fifths. In the complete subgraph, we have every degree is 4, so this is x4 to the fifths. Okay. And for instance, if you want to count the number of perfect matchings, you just plug in 0, 1, 0, 0, 0, 0 into this, because a perfect matching is a subgraph where every degree is 1. So if you plug in 1 at x1 and 0 everywhere else, then it will count the perfect matching. Also, I will need this slightly more general thing that I give a weight z to it, but actually this is again just a evaluation. I'm running out of time, so I just explain what's going on. The first thing that actually you can encode this ZGN mu as an evaluation of the subgraph counting thing. An even more interesting thing that you do not only can encode this ZGN mu as an evaluation, but actually you can evaluate it in many different ways. So for every t in a 0 to pi, you get an evaluation. And Okay, I skip all these things. I try to explain what's going on in an example. So suppose degree is 8. So we have an 8 regular graph. Q is 5 and W is 1. Then if you evaluate FG at this vector, which is 9-dimensional, then you get one evaluation. And this very first number is actually the rank 1 approximation. But actually, you can do a better thing. You can use another angle. You get another vector, and you also get an evaluation. So if you evaluate this FG here, then you get again this model rank 2 approximation for this one. Here, the first coordinate is actually the maximum of this trigonometric polynomial. And if you consider the sign structure, you can even realize that this must be a lower bound because at odd degree we see a negative number and even degree a positive. But if you consider a subgraph, the number of odd degree vertices is even, so the minus signs just cancels. Okay, so that's why we get a lower bound because somehow we can use a vector. Yes.
I mean, just to keep track of them, you have approximately 4.
Okay, or yeah, I'll try to wrap up as fast as I can. Yeah, thank you. So that's why there's a lower bound, and also this will be the limit. So this value. So what happens that you have a lot of vectors, each evaluation, and you just consider the first coordinate, and where the first coordinate is maximal, that will be the limit, and also a lower bound. Yeah, I skip it. Also this one. Let me mention a fun thing that there is a T1, so also another thing where all zeros of this FG vector with this extra Z has zeros on a circle, and this will give us the limit thing. So this Li-Yang theorem somehow transforms into the limit. Probably I skip this, how technically works that we have a measure on the circle, and then this measure will converge, and then we get a limit for that. This is how on the phase transition looks like this trigonometric function. So at the phase transition, we have two maximum. They have the same number evaluation, and this is symmetric for this thing. So this trigonometric function, which I showed at the very beginning, is very, very nice for the phase transition. And for the phase transition, the radius of this circle, which I showed you, is 1. So that's how you describe it. And that's all. Thank you very much for your attention.
Thanks for very interesting talk. Are there questions? And maybe while we are taking questions, the next speaker can set up. So questions.
So sort of following one of the previous questions. So what are the challenges to extending this to general degree distribution graphs? I mean, the regularity, is it just the explicit constant at the end?
So I use the regularity in the analysis of this rank 2 approximation. Probably this part should be somehow reworked, but I think this should be doable. So it's just very convenient because you can use this Li-Yang theorem and zeros on the circle and limit measures.
This is not directly related, but is there any reason or motivation to look at the case when Q is also growing with n? Because as you mentioned, most of the work or all of the work works with Q free of n. Is there any reason to look at the other regime?
Which Q? Sorry.
Oh, the number of colors.
Oh, I see.
Sorry.
I see. Yeah, it's not clear. Yeah, it's not clear. Actually, one thing is interesting that if Q is between 0 and 1, the model behaves completely differently than for Q bigger than 1. So that's how it much more related to the number of forests and spelling trees. So this is completely different, and we don't have it.
I was thinking more about the birthday problem when you have lots of, when the number of colors is large, but we can talk later maybe.
So you're mentioning the phase transition is first order when you were strictly forward to 2. How is this for Q in between 1 and 2? Is it second order there? Do your results apply?
So when Q is between 1 and 2, we have only conjectural result actually, and the phase transition is at the different value. So I draw this picture. Yeah. So I had this picture. Here we have Q equal to 2. This Q is x minus 1 times y minus 1. Here that this other hyperbolic Q is equal to 1. Here we have x is equal to d minus 1. And then we have this. And now the phase transition here is at this point and not some contention of this. This is actually the percolation. So 1 over d minus 1 is the percolation threshold, and this d minus 1 is that.
But do you know whether between Q and 1?
We didn't check it. Actually, for here, all results are conjectural here. So we have conjectures, but yeah, here we know.
Maybe in the interest of time, we can have questions.
Thanks very much.
So our next speaker is Dan Kral, and we'll be learning about analytic approach to quasi-randomness.
So I think I'm ready. Can you hear me? I guess it's mostly the question for those who are not here. So but it's happy that those who are here